Hello everyone. I am Hasini and this is Team EcoSpot and we are excited to present our project Skyworld under the theme of renewable and sustainable energy at the Smart India Hackathon 2025. Our problem statement ID is 25116. Title Student Innovation Swadeshi for Atmanirbhar Bharat Renewable and Sustainable Energy. The theme of our problem statement is renewable and sustainable energy under the hardware category. This theme resonates deeply with India's vision of building an Atmanirbhar Bharat by promoting indigenous solutions and address global challenges in every sustainability. Today, we are here to present our project Skyvolt, a laser based wireless charging system designed to transform the future of sustainable energy in India. Let us begin with the thought of experiment. Imagine a world where charging your phone, your laptop, or your drone, or even your electric vehicle is as seamless as connecting to Wi Fi. No cables, no plugs, no searching for power sockets in the middle of a mission. This is the world we are striving to create, a world where energy is wireless, sustainable, and omnipresent. But first, let us look at the problem we are solving. In today's digital era, our dependency on devices is undeniable. Yet, our devices are only as useful as their battery life. Charges and cables tie us down, limit mobility, and add us clutters. Now imagine a drone flying over a disaster site suddenly forced to land just because its battery ran out. A medical team in a remote village undertook cable essential equipment because the grid is unreliable. Thousands of IoT devices in a smart city going offline one by one because their batteries need manual replacement. These are just only small inconveniences, but they are very critical challenges, and conventional charging methods cannot solve them. India, on its journey to becoming truly Atmanirbhar, needs scalable indigenous solutions that reduce dependency on imports, enable energy self-sufficiency, and empower innovation in renewable technology. This is why we want to create Skyworld. So, what is exactly Skyworld means? It is a laser based wireless charging system that transmits energy across distances safely, efficiently, and sustainably. Let's see how it works. A laser transmitter converts electrical energy into a focused beam of light. Here, the transmitter, as a laser source, converts the beam, sends it to the receiver. Next, on the other side, photovoltaic receiver cells capture this beam and convert it back into electricity. This system is enhanced by precision optics, sensors, and microcontrollers that ensure alignment, regulate power flow, and generate safety. Everything here is integrated with software intelligence written in C++, Python, and simulations coordinated through ROS and IoT protocols for real time tracking and monitoring. This is not just a theoretical model. We want to build and test a prototype working using a 10 watts laser diode, PV cells, DC to DC converters, and smart firmware. It works, it charges, and it proves the concept. Now, why is it different from the existing wireless charging solutions? Firstly, the range. Traditional inductive chargers work only across centimeters, but the Skyvolt can deliver power over meters of distance, enabling real mobility. The main thing is long range wireless charging. Next, the energy density. Focused laser beam ensures minimal loss, making it more efficient than radio or microwave based systems at this scale. Next, autonomous beam tracking. Using sensors and real time alignment, the system can adapt even if the receiver moves slightly. Next, the scalability. From IoT devices to drones, from medical kits to EV infrastructure, Skyworld can adapt to multiple applications. It is not just a single thing, but it can be used in many applications. Now, let's go deep dive into the technical approach. Let's take a closer look at the technical foundation. Firstly, the technologies we are using. First, in the hardware components, we use a 10 watts laser diode as the transmitter. A photovoltaic receiver cells at 1080 nanometers wavelength, 3D cameras and sensors for tracking the alignment, DC to DC converters for efficient power regulation, a microcontroller to coordinate, control, and monitor the thing. Next, the software tech. Here we use firmware written in C or C++ for hardware integration, Python for simulation, analysis, and optimization, ROS and IoT protocols for real-time monitoring and wireless communication. Next, the methodology. Design. Firstly, we have to select the components we require and optimize the system design. We need to select the suitable laser and suitable PV cells based on the power needs. Next, the prototype. Building the transmitter, optics, receiver, and the control system. Software integration. Embedding firmware, tracking, and monitoring tools. Next comes the testing. Here we need to measure the efficiency and see the range. And we shall check whether it is in safety and check whether it is in under the different conditions or not. Next, the validation, demonstrating charging of real devices wirelessly. This structured approach ensures our system is practical, reliable, and scalable. Now, let's explore some real world scenarios. Defense and UAVs. Unmanned aerial vehicles can stay airborne longer, recharging wirelessly mid mission, no downtime, no landing. Smart cities. Air quality sensors, traffic monitors, and public safety devices can operate continuously without manual charging. Disaster management. Rescue teams can power medical kits, lighting, and communication devices wirelessly, even in regions with no grid. Rural electrification. Villages can receive power wirelessly, bypassing the need for expensive grid infrastructure. Consumer devices. Imagine your phone charging while you use it without cables or plugs. Each of these cases demonstrate how Skyworld can redefine energy delivery. Some of the limitations are its efficiency, line of flight requirements. So we have to see that nothing obstacle comes in front of us, and we have to continuously check the PV cell performance. Economic feasibility. At the starting, it is high to cost bear, but slowly we can reduce the cost. Cost effective at the scale. Next, operational feasibility, technically practical and safety and tracking. The main potential challenges and risk. No innovation comes without challenges. Some hurdles we faced include beam alignment, keeping the laser precisely focused on a moving receiver, efficiency losses, optimizing conversion rates between laser and PV cells, safety concerns, ensuring the laser is safe for humans with built-in cutoffs, scalability, designing the system to move beyond prototypes into real-world deployment. Through iterative testing and refinement, we addressed these challenges developing tracking algorithms, safety protocols, and scalable designs. Cost factors. Need for high quality lasers is also one of the potential challenges and risks. Impact and benefits. Benefits of the solution. Social impact provides energy access improves convenience for everyday users, enables faster response in emergencies. Next comes the economic impact. It reduces downtime in industries and defense. It also cuts infrastructure costs by minimizing the cabling. It creates opportunities for startups in the wireless energy sector. Next comes the environmental impact. It reduces e-waste from discard cables, chargers, and disposable batteries. It minimizes carbon footprints through efficient delivery. It complements renewable energy systems, making them more accessible. The main potential impact on target audience is smart cities and industries 4.2, consumers and IoT users, space and defense agencies, drone and robotics industry. Now, let us have a look at the work we have done. This is the circuit diagram we have created, and one of the application is charging drone in midair. Here there are two parts mainly called the transmitter and the receiver. In the transmitter we have placed a 3D camera or a tracking system for tracking the receiver directions or the dimensions. This tracks the speed of the receiver and sends it to the Arduino or the microprocessor where this code will be running and sends it to the server or the servo motors or the sensors, and sensors it and send to the laser so that the laser emits the beam onto the receiver. Here photovoltaic cells are present to capture the photons which are generated by the laser. Next comes the combination based on drone battery, and this makes the DC to DC converter. Here a coolant system is placed to cool any of the heat is produced so that it does not damage any internal parts. Next comes the indicator of the drone charging. Now let's see more into the prototype. Now let's see the prototype. Wireless charge transfer using laser simulation. Here the main power source is the battery 1. Here we have placed a 9 volts battery. This provides the input DC supply to the power to whole circuit. Next, the voltage regulator section. This is named as U1 LM317T. This is an adjustable voltage regulator. It is used to set a stable output voltage that powers the laser diode. Here there are 3 pins. Pin 3 V in, input from the battery, and the pin 2 V out, regulated output. Pin 1 is for adjustment, used to set the output voltage. Here there are two resistors, namely R1 and RV1. R1 is of 330 ohms and RV1 is 1 kilo potentiometer. Together they form a voltage divider to adjust the output of LM317. Turning the potentiometer changes the laser diode's supply voltage. Hence, there are two capacitors, namely C1 and C2. C1 is of 0.1 microfarads and C2 is of 1.0 microfarads. These are bypass capacitors to reduce noise and stabilize the regulator. Next comes the laser diode driver. The output of LM317 goes to the laser diode shown as a LED symbol in U2. When powered, this laser emits light that carries energy wirelessly towards a photovoltaic receiver. Receiver receives the photons from the from the light and from the photovoltaic cell to the load. PV cell or the solar cell. The laser light falls on the solar cell which converts the laser energy back into the electrical energy. Load resistors RL1 and RL2. These represent the device being charged, like a battery or small electronic device. The converted power from PV cells flows through these loads. The working principle is the 9-volt battery powers the LM317 regulator and provides a stable adjustment DC voltage to the diode. The laser diode emits a laser beam instead of electrical wires. A photovoltaic cell at the receiver converts the laser energy to the electrical energy. This recovered energy is delivered to the load resistors RL1 and RL2, simulating wireless charging. Now let's look into the circuit. Here, the image is shown. The breadboard has a laser diode module glowing red. Wires connect the circuit to the regulated DC supply. Right side, a digital multimeter is connected, most likely for measuring the voltage across the laser diode or the output at the receiver, solar cell or the load. The purpose of the laser divider circuit. The term divider here refers to using a voltage divider circuit to control the input to the laser diode. Too much current can burn a laser diode quickly. By using resistor plus potentiometer, the supply voltage is adjusted before feeding the laser diode. This ensures safe and stable operation of the diode. The laser beam on the receiver side, photovoltaic cell receives, and the multimeter shows the how much of current or the voltage is produced. In simple words, setup is your laser divider circuit, the supply, divider and the laser diode. Now let us see one of the application. Charging drone in midair using laser transmission. Here we have done this simulation using the Blender app. Here an laser emitter is produced and a drone is also produced by us. Now let's open the file of the Blender. Let's see the application we have done on the Blender. See here, laser is emitted onto the drone and the photovoltaic cell receives and sends it to the laser. These lasers are produced at very high density. To increase the density, we use an optical amplifier so that it increases the laser density to the 10 times to the 10,000 times. See, in all the directions it produces the laser beams and current is flown to the so that the drone will not stop at any time. It starts moving continuously without anything. Now let us look into some of the research papers. This is laser based solar power transfer for low power applications. See, all these things are done on the research. Now let's look at one of the block diagram. Here solar panel receives the sunlight onto the photovoltaic cells, and the light is captured and sent it to the battery, and the voltage regulator regulates the voltage and sends it to the laser. The laser emits the beam to the photodiode, and it sends it to the any of the machine or the device. See, the sunlight falls on the photovoltaic cell and the photons are emitted due to n-type silicon or p-type silicon, and the electron flow and sends to the photovoltaic receiver, captures the photons and converts the light energy into the electrical energy. This is the batteries to store the solar energy we use, and this is the photodiode. And this is the laser diode which emits the laser out. This is the laser diode driver circuit. This is we have already seen LM317. We have seen three pins. This is pin 1, pin 2 and pin 3. Pin 3 get the input from the battery. Pin 2 sends the output to the laser and adjustment is done for the voltages. Here see, adjust output and input. A project is done and analysis is done on that so that the laser is emitted and it is used in some cases. Let us see one more research paper. This is the study on battery charging converter for MPPT control of laser wireless power transmission system. Here, MPPT stands for maximum power point tracking. It is a control algorithm used in photovoltaic systems such as solar power systems to constantly monitor and adjust the electrical operating point, voltage and current of the solar panels. The goal of this MPPT is to ensure this solar array operates at its maximum power point MPP, where it produces the highest possible power output, thereby maximizing energy conversion efficiency under varying environmental conditions like sunlight intensity and the temperature. Now let us see one of the picture. Here, the laser is emitted out and sent to the drone. Here, the photovoltaic cell receivers receive the light energy as the photons, and then the photons are converted into electrical energy and sent to the drone. So that the drone will not stop at any of the place and continuously flows. Here, laser emitter emits the laser beam. Here, the wireless optical power transmission takes place. Photovoltaic cell captures the photons and sends to the battery charging converter, and a lipopolymer battery, that is lithium polymer battery, is used and sent to the target device. Here, one more thing is this is the photovoltaic cell module. Here, there are total 16 cells connected in series. And this is one of the graph for current, voltage and the power, and this is irradiation for one case and another case irradiation. This is the boost converter for battery charging with laser PV modules. Here one more experimental setup for laser wireless power transmission. Here an electronic load, a battery and a laser PV module, laser source and an oscilloscope is placed. Here, laser beam module emits the laser and electronic load is used for the generation of the laser. And the oscilloscope scopes it and the and here the receiver has a laser PV module, battery converter, electronic load, current probe and a battery. Here see. This is the prototype boost converter configuration. Here the input is taken in and the output is given out, and here the boost converter takes place. So the experimental result of maximum power point tracking control of laser PV module for battery charging. Now let's see some of the research and references done already. Here, let's consider three cases where laser wavelength and the band gap wavelength are almost similar. When they are similar, the photon is sent onto the conduction band, and on receiving on the conduction band, an electron is excited out. Almost all photons generate electrons in this case. Next, in the case 2, the wavelength of laser is less than the wavelength of the band gap. When the photon is sent onto the conduction band, electron is emitted out, but there is some thermalization loss. Here, extra energy is lost as heat. Here, there is some loss. In the case 3, if the wavelength of the laser is more than the wavelength of the band gap, photon is sent onto the conduction band, but no electron is emitted here. So photon cannot excite any of the electrons. In this case, emitter electric power is sent to the optical source, something like the laser or the LED. In an optics lens and optical amplifier is used. Here optical amplifier means which increase the density of the laser to the 10 times to 10,000 times. And wireless optical power transfer is done here, and the receiver receives the laser and it sends to the target device. Now let's see some of the research papers.